All right, so in this portion, I want to tell you guys about the second work type of problems that involves gravity and emptying a tank of a certain shape uh, that is filled with some sort of fluid. And my example today would be water, and that's similar to what your book offers, but it could be any fluid. As long as they give you the information about mass density of the fluid, it really doesn't make a difference what it is. It could be any fluid, oil, water, whatever, as long as they tell you what the mass density of the fluid is. So basically, the setup of the problem is actually pretty straightforward. You have a tank of a certain radius. So we say that you have, if this is the center of the tank, we assume that the radius of the tank is, say in this case, 5 meters. Again, it's not relevant. As long as I could change 5 to anything, and the problem would be similar process, just the different numbers. And suppose that for the sake of this example, I have a pump on top of the tank that empties out the fluid outside of the tank. And and the pump is able to go all the way to the bottom of the tank and suck the water out to empty out the water. So it's again it's a simple idea, but we're trying to figure out how much work is done, and we're assuming again the tank is filled with water. Now, other questions may say it's half full with water, or it is only up to a certain level that's filled with water, so it's not all the way up. It only changes bounds of the integral. It doesn't really change the setup or anything I'm going to do after that. And the problem also gives you that the mass density of the water is 1,000 kg meter cube. So you're already given that too. So again, as I said, this is the part that the problem would have to give you. It would say, well, you're using some sort of oil, and the mass density of oil is 900 kg per meter cube, or something like that. So they will have to give you that information. Of course, G, the gravitational G constant, is 9.8 meter per second square. So that will also be either given to you, or hopefully you know this. If it is for feet, it will be 32 feet per second square. So it would be also an information that will be shared with you. So let's get started. So knowing that if I have water in this tank, at each time I'm going to have to empty out a layer of the water, and that kind of leads us to partitioning our tank. So these are the partitions. So this could be your x0 on the top, and this could be xn at the bottom. And of course, x0 is 0 and xn is 10 because it's 10 meters long. It's 5 meters in between. Each layer of the water looks something like this. Of course, it's a circular disc, and then I can actually flatten it to make sure that it is actually a disc. Okay. So what I need to do is to figure out what is the work. I know the work done is going to be the distance this water has to go up, which is really just going to be your xi, because that's how far away you are from the pipe. If this is the ith disk of water. So that's the distance. And then you multiply distance by force. Again, going back to the force times distance, right? So work is force times distance, displacement. Our displacement is xi. So if I want to calculate wi, the ith work for the ith layer of water to be removed, wi, is fi, is the force of that required for that layer to be removed, times the distance that layer is going to move, which is going to be from here to the pump, whatever that distance is. So far, it's okay. So now what I need to do is I need to calculate parts. I already have the distance, so that's not a problem. I need to figure out what my Fi is. So let's see, what would Fi be? Fi is the weight of the water. And of course, the weight is mass times 9.8. So it's going to be Wi, but let's call it actually just weight. Weight of the ith layer, which is going to be the volume of the layer times mass density times 9.8. So this makes it weight density and this makes the weight or the force that you need. Okay, so volume is a tricky part. Mass density, of course, is 1,000, and 9.8 is already here. So this. So we need to figure out the volume part. The volume is delta x, which is your height, and now I have to multiply by the cross-sectional area. Okay, all right, let's look at this again. Now, the cross-section area, if I draw a radius like this is r, which is 5. From here to here is xi. So this side is going to be 5 minus xi. And this is, of course, is ri, and that's what I want to calculate. So ri squared is, actually, let me write out the full formula. Ri squared plus 5 minus xi squared is equal to 5 squared. Or ri squared is 25, which is your 5 squared, minus 5 minus xi squared. And remember, the cross-section area is pi ri squared, pi r squared. This is going to be pi times ri squared, which is 25 minus 5 minus xi squared. Okay, that can be cleaned up a little, actually a bit, a lot. It's 25 minus 25 plus 10xi minus xi squared delta x. So once again, pi ri squared is your cross-sectional area, times delta x gives you volume, times 1,000 gives you mass density, times this is total mass, times 9.8 gives you total weight. So it's going to be 9,800 pi. So I just did this part on pi times 25's cancel out, 10xi minus xi squared delta x. So that is the work required for just one layer of water to be moved. Just one layer of water to be moved, this layer, the work done is this. Now this is the force of it. Now multiply that by xi gives you the work. So wi is 9,800 pi 10xi minus xi squared xi. So this is force along with delta x, and this is distance. So total work would be sum of those approximately, because remember why approximate? Because I had to flatten the width, also because there's going to be different volumes, right? As you get, yeah. So work is approximately sum I equal to 1 to n of 9,800 pi xi 10 xi minus xi squared delta x. Taking the limit, the integral, so you get 0 to, it's exactly equal to 0 to 10. Why 0 to 10? Because 0 to 10, 0 to 10. So it's going to be 0 to 10, 9,800 pi x, 10x minus x squared dx. Going through the calculation, 9,800 pi, 0 to 10, 10x squared minus x cubed, which is 9,800 pi, 10³ x cubed minus 1/4 x to the 4, which is going to be 9,800 pi. Yeah, you just have to go through it. 1,000 times 10, 10,000. 1/4 of 10,000 minus 0. So it's going to get 1/12 of 10,000. And if you just do the calculation, simplify the calculation, you get 9 point, actually, so that's going to be 2450 times 10,000 pi over 3, or 2.45 times 10 to the 4 here and 3 here, 7/3 pi. That's going to be how much work is done in removing all that water from the tank using a pump that's on top of the tank. Now, so if I modify my question but slightly and say, okay, you know what, I'm going to start, instead of going from top of the tank to the bottom of the tank, I just want to know how much work is done doing half of the tank. Then all that would change is, instead of going from 0 to 10, you would go from 5 to 10. So if it's just the bottom half of the tank, if we want the work done by the bottom half of the tank, by the pump, sorry, emptying the bottom half of the tank, all it would do, it would change the bounds. Instead of from 0 to 10, it goes from 5 to 10. Everything else stays the same. No problem. And you would have to calculate that. But if it's the top half of the tank, then you would do that as well. So if you focus, the main issue here was actually geometry. The rest of it is not bad. We already knew that work is force times displacement. Force now is going to be how much force it will take for a layer. The gravity pulls the layer down. The pump has to fight that and pull it up. So it has to be equal but opposite direction, right? So gravity applies a force of layer, which is equivalent to the weight of the layer of water. So I need to find the layer of the ith layer, weight of the ith layer. Weight is volume times mass density. That gives you total mass, times 9.8 gives you total weight. And again, 9.8 is the gravitational constant. So 9.8 stays. Mass density was given to you by the problem. Both numbers were actually given to you by the problem. It's 1,000. Volume of the layer is going to be the cross-sectional area of the layer, which is pi r squared, times the height of the layer, which we will designate to be delta x. And of course, we take the limit as delta x goes to 0. Now, the RI part is really the geometry that you need. And again, there's only a couple of things here. Either for some problems, you may have to use the Euclid's law of similar triangles. Some problems you use the Pythagorean theorem, like here. So it depends again but there are not many formulas you have to use. Ri, the cross-sectional radius, is 5 squared. Ri squared is 5 squared minus 5 minus I squared. So that's how you get this. So you get pi times that, delta x, and then 1,000 times negative. And again, the rest of it is just algebra simplification. So weight is this after simplification. I'm sorry, work. Sorry, this is not work, because work is this times distance. So force times distance. So capital W is going to be the sum of all those approximately. And then if I take the limit as delta x goes to 0 and as n goes to infinity, I get it in the form of an integral. And then of course, that's the rest of it is just calculating the integral. Now, as I said, you may have the tank problem like this. Your book also talks about a conic tank that looks like this. Again, the pump is on the top. Now, similar problems, we put the top pump at the bottom and says how much work is done by the pump filling out the tank. So instead of emptying the tank, now you want to fill out the tank. So that's the similar process. But for this one, you have to, instead of using Pythagorean, and I'll let you guys look at the example, but instead of using Pythagorean theorem, you have to use law of similar triangles, Euclid's law. And remember, for similar triangles, if two triangles are similar, then the ratios of their sides, if this is A, B, C, and this is A prime, B prime, C prime, A to A prime, and B to B prime, and C to C prime should stay constant. That's Euclid's law for similar triangles. So that's how it is. So this and this, so the ratio of this to this is the same ratio as this to the whole thing, is the same ratio as this to the whole thing. So those don't change. Okay, so I hope this kind of helps you. There are other shapes as well. There is a shape for like a trough in example number, problem number 23, for example. So it draws you a trough, and then it says, okay, you want to empty it. That's the same exactly thing, but now your layers of water will look like that. So you have to just calculate this cross-sectional area times the length or the thickness of the layer to figure out the volume. They multiply the volume by mass density, multiplied by 9.8 to get the weight density. And then, and those problems, some of them are in feet, so you have to calculate them. And for water, for example, the weight density of water is 62.5. Is 62.5 pounds per feet cube. Per cubic feet. So that's another one. So I hope this is now gives you some guidance on how to approach the tank problems. Again, it's a lot of geometry. Now you may want to watch this a couple of times just to see what I did there. But they're not really beyond that. It's just a basic geometry, and it's either triangular, a Pythagorean theorem, or it's a similar triangles or such. So it's kind of like the main idea here is the work is displacement times force, and the force is the variable factor. And of course, it's always the displacement, but displacement is like in this case, it's just xi. It's not that hard, but the force is the one that changes for every xi. So you have to have that in mind. Okay. So I hope this helped. Again, post your questions for me to do for you guys as I do the homework session for you. But at this point, I think this should get you started to be able to do 6.4. I'll read ahead 6.5 if I were you. It's 6.5 is actually pretty straightforward. It's just one formula. But I don't want to mix lectures, so I have a lecture for that as well for you guys to watch before too long. And I thank you for your attention on this one.